You ever wonder how your phone just knows what you're about to type? Or how a bank can prove a loan in like seconds? Well, that's all machine learning. But what does that even mean? Okay, let's dive in and really break down how we actually teach a computer to think.
I mean, it really does feel like magic sometimes, doesn't it? But it's not. It's a process. It's a bunch of rules and a ton of data that all lead to a very specific outcome. So the big question we're going to tackle here is this: how does a machine actually learn?
So the first thing you've got to understand is that machine learning isn't just one single thing. It's more of an umbrella term. Broadly speaking, there are two main paths, two different ways a machine can learn from the data we feed it. Think of it like two totally different styles of teaching.
And here they are: supervised and unsupervised learning. And you know what? The core difference is actually pretty simple. With supervised learning, we give the machine examples that are already labeled, which just means the correct answer is already there. It's kind of like studying with an answer key. With unsupervised learning, the data has no labels. We just dump a whole bunch of information in front of the machine and basically say, go figure it out. Find some patterns.
For the rest of this explainer, we're going to zoom in on the most common type, and that's supervised learning. The best way to think about it is like a student learning with a teacher. You show them a problem, you show them the right answer. You do it over and over and over again until they start to get the logic for themselves. So here's the key takeaway. The machine is learning from a history where we already know how things turned out. Imagine a bank building a system to approve credit. They'd feed it thousands of old customer applications where they already know who got approved and who was denied. The machine's job is to learn the connection between all that customer info and the final decision.
Okay, so if we're going to teach a machine, we need to speak its language, right? There are a few key terms we have to get our heads around to really see how data is set up for learning. This is kind of like the basic vocabulary you'd need for any machine learning project.
So the first word to know is an example, or sometimes people call it an instance. It's just one complete record of whatever it is we're studying. So one customer's entire application for a loan, that's one example. A single patient's complete medical file, that's another example. Honestly, the easiest way to picture it is just as a single row in a giant spreadsheet.
Right, so if an example is the whole row, then an attribute, you'll also hear called a feature, is just a single piece of information in that row. If our example is that customer, the attributes would be things like their age, their income, their debt. In our spreadsheet world, these are just the individual columns. And then we get to the most important piece of the puzzle, at least for us right now, the class. This is that one special attribute that we're actually trying to predict. In our bank example, the class is that final question, credit approved, yes or no. This is the answer, the label, that makes it supervised learning in the first place. All right, so let's put all those pieces together and see how it looks. On this table, every row is an example, a different customer. The columns for age, income, and debt, those are our attributes. And that last column, the one we're trying to figure out, yep, that's our class. This is exactly how we structure data to teach a machine. See? Not so complicated. Okay, so the machine can learn to make a prediction. Great. But how is it making that prediction? This brings us to another really huge idea: the difference between systems where the logic is a total mystery and systems where we can actually see what's going on.
So on one side, you've got what are called non-symbolic or black box systems. You put your data in, an answer pops out, but you have absolutely no idea what calculations or logic happened in the middle. Then on the other side, you've got symbolic or glass box systems. These actually create something we can understand, like a set of rules or a decision tree that a person can look at and follow. Basically, they show their work.
And hey, this is not a new idea. A pioneer in the field, Richard Mikulski, was arguing this way back in 1983. He said the goal isn't just to get the right answer. The result should be directly interpretable in natural language. In other words, what's the point if we can't understand why the machine made the decision it did? We need to be able to trust it.
So we've got our label data, and we've decided we want a model that we can actually understand. So how do we do the teaching? Let's walk through the actual process of training the machine, of turning all that raw data into a real decision maker.
So how does the learning part actually happen? Well, the magic is in a program called an inductor. This is the learning algorithm itself. Its whole job is to sift through all our labeled examples and come up with a hypothesis, a set of rules for making decisions. And that final product, the finished model it spits out, that's called the classifier. And this lays out the process perfectly. First, you start with all your data. Now, this next step is absolutely crucial. You don't use all of it for teaching. You split it into a training set and a test set.
Then you feed only the training set to the inductor. The inductor does its thing, analyzes all that data, and boom, it produces your classifier.
So we've built our model, our classifier. But is it any good? Did it actually learn the right lessons? Or did it just kind of memorize the answers from the training examples? This is where that test set we saved earlier comes into play. It's time for the final exam.
And this is a super important distinction, the difference between apparent error and true error. See, if you test the model using the same data it trained on, you'll get its apparent error. But that's like giving a student the exact same practice test as the final. Of course they'll do well. The true error comes from testing it on the test set on data it has never ever seen before. That tells you how it's really going to do out in the wild.
Just to make this really concrete, let's imagine we have 500 total customer examples. We'll take a big chunk of those, let's say 400 of them, and that becomes our training set. This is the stuff the algorithm gets to study from.
And then we take those other 100 examples and we lock them away in a vault. That's our test set. Only after the model is completely built do we bring out these fresh examples for its final exam. This is the only way to know its true performance.
Which brings us to one last, really fascinating question. Let's say our machine aces its test. It gets a 99% accuracy score. Incredible, right? But if it's a black box and we have no idea why it's getting those answers right, can we really say it understands the problem? Or is it just an incredibly sophisticated pattern matcher? That's definitely something worth thinking about.